Okay, so we have this bar, we have a mass on a 1 meter track, and it's moving up and down over a period of about a second from between 0 and 1 meter. And so what would that look like? Well, it rises in about 0.3 seconds and then falls over a period of about 0.6 seconds. So it would look like about like this. And so we want to see what the velocity is as a function of time, given the displacement. I can start with the easy part. The velocity is 0 wherever it's flat. So it's going to be 0 here, and it looks like it's flat here. Here the velocity is very positive. This is probably the sharpest rise, and this is probably the sharpest drop. And so this is very positive, and this is negative, but it's less negative. Do you see that this drops over a period of 4 seconds, and this rises over a period of 2 seconds. So the top velocity is going to be positive in this direction, and this is going to be the top negative velocity, which will probably be about half as great. It will be about like here. And let's find out what those numbers are. Okay? So what we can say is, we draw a tangent to this. I remember in high school doing this stuff, right? It moves about 1 meter, rise over run, in about, that's a little bit less than 0.2 seconds in my graph. So the speed is about 1 meter in 0.2 seconds. That would be on the order of 5 meters per second. Maybe it's a little bit greater. And this one will be on the order of -2 meters per second. And so how do we get there? Well, does it rise up abruptly? No, we can see that the slope of this line is the velocity. The slope starts at 0 and moves smoothly to that higher velocity. And then it drops down to 0 rather smoothly as well. Now, you might say, I think there's a constant velocity right here. This was pretty straight, and so I don't agree with you, Pete. And so in that case, it would look more like this, with being flat on the top, indicating a constant velocity. And here the velocity is 0. Here the velocity is already negative, so I would say that this drops off, continues to drop off, and then this is pretty constant velocity right there. So I would say this velocity is pretty constant, right? And the velocity drops to 0 between here and here. So it would go something like that. And then you say, all right, I begin at the bottom at 0 meters, and I finish at 0 meters. So the area under this graph, meters per second times seconds, it should be 0 because there's no change in displacement over the whole time. And you could say, does this area equal this area? Well, this is about twice as high, this is about twice as long. I'm good with that. Now how about the slope of the velocity? Because the acceleration is the slope of the velocity. And I can see it's positive here, pretty positive. Here it's 0, because it's flat. Here it's pretty flat. And here it's positive again. As positive as that? Maybe not. Okay? But here it's very, very negative. So I would say, around like here. Does it go to 0 to negative abruptly? It's really hard to tell from that graph. So I think it's reasonable to make a graph that looks something like this. The slope looks pretty constant here, so I'll make this pretty flat. Then the velocity seems pretty constant right here, so maybe this is flat again. And this is very, very negative. Very, very negative. And then here is pretty flat. And here it's kind of positive, but not near as positive as here. So this is what I would see. And what would those slopes be? So acceleration is equal to change in velocity over change in time. And I go from 0 to 5 meters per second. That change is 5 meters per second. And the period of time is slightly less than 0.2 seconds. So maybe it's 0.15 seconds. And so this would be on the order of 30 meters per second squared. And so I could graph here, this is 30 meters per second squared, this is 0, and maybe this is twice as much. This might be negative 60 meters per second squared. And again, I start at rest and I finish at rest. Is the area under this graph 0? It doesn't look here like it is because I wasn't able to go deep enough to show that I had really negative acceleration here. This is about twice the slope of that, so we should really drop down below the board, and then we would see that this positive area here and here would be about compensated by that negative area. Okay, so let's go back and look at force. How would we graph force? And why would there be force? This thing's moving up and then accelerating down. It only accelerates down right here, right? It's moving up, it's going up, and accelerating up fast, accelerating down. It's only accelerating down because there's a force downward on it. So that negative acceleration is caused by a downward force, and this is going to be as simple as just multiplying by the mass, because the mass is equal to 5 kilograms, so the force is equal to mass times acceleration is just 5 kilograms times whatever I had there. And so I could make this a force graph. Force is equal to ma by just saying that this is no longer 30 meters per second squared, but it's 150 kilogram meters per second squared, or 150 newtons, and then this would be minus 300 newtons. Okay, that's a reasonable force to be putting on 5 kilograms, right? This would be the force of gravity acting on 15 kilograms, or 33 pounds, in order to change its velocity as fast as it does. How about the kinetic energy? It's equal to 1/2 mv squared. And so 1/2 times 5 kg times v squared. My maximum velocity is about 5 meters per second. We square that. 25 times 5 is 125, divided by 2 is like 63 kilogram meters squared per second squared. And so this would be my kinetic energy, my maximum kinetic energy, when I'm at this maximum speed. So let's change, can we change this graph to kinetic energy as easily as we changed the acceleration to force? And the answer is no, because there's not a linear relationship between velocity and kinetic energy. It's a quadratic relationship. So let's go in and calculate the kinetic energy here as well. If it's only 2 meters per second, that squared gives me 4 meters per second, 4 meters squared per second squared, times 1/2 is 2 times 5 is 10. So this is only 10 joules here, where this corresponds to 63 joules. So let me make another scale where this is 70 joules. I'm going to graph the kinetic energy here, and this would then be 70 joules. Oh, no, man, there's no negative, right? Because kinetic energy is always positive. And so rather than be a straight line, this linear relationship would turn to a quadratic relationship. And this as well would be quadratic. Now, this negative kinetic energy, no, it's mv squared, so it would be positive as well here, but this would only go up to 10. So this would look much flatter and go to 0 quicker. Okay, now how about the maximum power? We remember power is equal to the rate of change of energy, and so that's going to be the slope of the energy time graph. And so you might pick this as being the maximum slope when the energy is changing the fastest. I won't pick that because that potentially is provided by brakes. This slope, increasing the kinetic energy, is certainly provided by a motor, and so we can make an estimate of this slope and see that I'm increasing by about 100 joules over a time period of about 0.1 second. And so it looks like it's going to be about a kilowatt. 10 to the third joules per second is a kilowatt.